when you go in already, or do you go in and for a book?
I usually know what I want, at least roughly. In some cases, I bring specific designs that I've like purchased and modified. There's a West Coast tattooer that specializes in like Celtic and Pictish spirals and like, so a lot of my pieces, like this is one of hers, this is one of hers.
Yeah.
So is that. So is this is a variant on. So I would bring a lot of things in and say, I need this inked.
So they'll do others. They don't just do their own.
Yeah. Right.
They'll do others.
Now, since I started, I've only gone to Jared for my last couple of pieces, and with him, I've been willing to say, because he's got a. The guys I had been going to were more like the neo-Americana traditional thing. So like, they were good artists, but they weren't going to do design for me in that style. Right.
A little bit more freestyle.
Right. Jared is a little more sort of simpatico with what I'm interested in. So in some cases, I would just like bring him ideas and say, this is what I want to do. He actually designed the. We had some back and forth on it, but he designed the Fudo sword that I had and knew what I meant when I said I want a Fudo sword. He said, "Oh, okay, yeah." So yeah, it's how that was going to go. So sometime this summer, I want to go ahead and do a piece here that I specified last year, and I want to go in and have him start like filling in around that and just like let him go with some of the tribal stuff that he does. And but he did a tribal Kefren, the Egyptian seraph god, for a friend of mine. Just stunning.
Something like that, like an 11-inch.
Amazing piece of
Two chest pieces. I have my rib cage.
Oh wow!
It's like from armpit to belt line. Like letters like this. It's my family name. Straight down, block letters. No shading. Just straight outline the whole way, right? That was the most painful.
I like a laptop.
All my tattoos. I felt like a scalpel the entire time.
Usually,
That's always.
I have a full back piece on. It's a Celtic cross with green and gray wine.
Designed
Yeah, that's true.
That's cool.
Although I haven't looked at my email today.
I guess.
I was there when he knew it for the first session. Pulled out the design and he came up and she was like, and I was like, oh, okay. Don't give it to her. Give it to me. Well, I don't have room for. I don't have any open room for anything like that.
Just
tramp God. I don't have room for that either. That's
I don't have
Or tablets on.
But I would.
When you're traveling,
He's really clean.
Yeah.
Thank you for metaphor because I figure out
Yeah, that was a little
The
weird.
great mystery.
Thank you.
We're delving into the great mystery.
Yeah, my back piece, because it's a cross, there's a very few open spots on my back, but they're all, I'm not willing to do my kidneys. I won't go over my kidneys because I know how much it hurt my side, my rib cage.
Yeah.
But it's shoulder blade to shoulder blade, neck to belt. It's a big cross.
Yeah.
And I did that and the shading all in one sitting.
Yeah, I've got one that's it's actually based on a Celtic cross. It's a runic piece, but it's the algae's rune. So basically, if you took the ring out and like folded it up, but it's got the inner links in the middle. And it's a good foot tall on my back, and we did that.
Centered?
Yeah, we did that shading in one session in 2006.
Yeah,
really different. Yeah, that's those.
I gave the guy that did the back pieces a very significant, because I got that done, my calf, and my forearm all done in one day. And I gave the guy that did my back a very significant tip.
So Becky Taggett identified, she's been doing a lot of that work. She found a package maybe 6 months ago that she really likes. It's an art package. It's got a clever name, but I can't remember
It's
what
like
it
for
is.
different.
Did you give the tip before?
After.
I think it's a
Never
package
tip before.
that does
Okay.
Becky Taggett.
Make it right? No, I don't know. So, can I email you?
Absolutely.
Yeah, I will email and ask for some, and I will come to CRC, and
Right.
maybe I ask Sean Price, because I analyze his data.
Yeah.
And he will come together.
I think it runs only on a Windows machine. And
Just repeatedly
so
stab
Becky
you.
has it set up on a Windows machine in our suite.
Yeah.
Like you say, you can come
Okay.
over, you bring your data.
Don't
and,
press the bottom button.
No.
Use the
Sorry,
software.
this one, I will mail you. Forward and top one, right?
Yeah, there's two buttons.
Right? So
Left and right.
it's this row in the middle, correct? One person. I usually press before I ask.
That's the point.
Yeah, right, that's advanced. Okay. Oh, yeah.
Oh,
Okay.
Yeah. I brought you that just in case you wanted it.
Oh, no.
Sure.
Okay.
All I can say now.
Oh, okay. Yeah, it is. Yeah, that came up.
Whatever, you know.
Because I can just say,
Is it going to blame you?
So I was like, oh, yeah, I know you too. I'm just so like, oh, I just wasn't just, I was hoping we have like.
Come and sit here.
Oh.
I know, right? Yeah.
Onward and upward.
I guess so, huh?
Yeah.
If it was me, I'd be moving to Hawaii. Like the Swedes. There's no accounting for taste.
You retirees, you think about that kind of thing.
That's right.
Those of us that have to
Can I
work
use
for
the
a
buttons to
living.
advance the slides? Sure.
Yes, sign pass, please.
I can skip this whole slide.
Yeah.
Alex, do you want me to use the microphone first?
I didn't.
Or do you care?
Yeah, doesn't matter.
Alright.
No, we don't, actually, you don't really need it, there's no one online.
That's so wonderful. Alright, well, we'll use it
Oh.
anyway, just in case someone pops up.
Okay.
So welcome everyone to the Technology Seminar Series. We have a presentation today, obviously, and next week, and then we're breaking for the summer. If anyone's interested in presenting next year, please let me know, or next fall, I guess, not really next year. There's a sign-in sheet going around. Please mark your name on there. It just helps us with the pizza, so that's very helpful and appreciated. So I'm pleased to present today's speakers. We have Alla Karnovsky, who is Research Assistant Professor in DCMB. Hani Habra, who is a graduate student in DCMB in Alla's lab, and Bill Duren is a bioinformatics programmer in Alla's lab. And they're going to talk to us about video.
Is that on?
Oh, did I not turn on? I forgot.
No, it's on.
It has to go up.
Now it's on, right? That's better?
Well,
Okay, perfect.
hi.
Good afternoon, everybody. So, as you heard, today we're going to talk about BINR. I'm going to explain what this is all about. And I just want to start by introducing a few people. So Marcy introduced, Hani, Bill, and myself. And there are two more people here, Maureen Ketchman, and she's right there, and Jan Wigginton, who are very much part of that team. So it has been a great collaboration, I think, between bioinformatics and Metabolomics core. And some other people were also involved. Peter was working and helping Maureen, and he helped us develop some of these features of the tool that we will be talking about, and of course Chuck Brandt, and have an ongoing collaboration with George Michaelides. Okay, so here's a brief outline of what I'm going to what we're going to try and do today, right? So I will try to talk about background and motivation, and then Hani will take over and talk about workflow, and Bill will jump in and we'll talk about some features of the software and performance. And so what we're hoping to do, if we can get through all the slides, we're actually going to try and sort of demo the BINR output, but our primary goal is to just sort of, first to set the stage to talk about why we need this tool in the first place, and then basically, to show you some neat computational solutions that were developed for this particular tool. So we don't talk about metabolomics here often in this department. I think we're mostly talking about genome and epigenome, and so this is just basically to kind of remind everybody that yes, there are metabolites, and so there are many things that are very cool about metabolites, and one of them is that they are perhaps the closest to the phenotype and to the function. And so, we have a metabolomics core here that is doing a beautiful job at measuring these metabolites in biological samples. And so I think that's sort of, the extent of my introduction. Right, so metabolomics kind of emerged in recent years as a high throughput omics science, right? And so usually the sort of common approach to analyzing the omics data, be it RNA-seq data or proteomics data or whatever. I mean, the usual approach that sort of seems pretty logical is to basically to make biological sense out of the data, is to map the your RNAs, metabolites, whatever biomolecules, to biological pathways. And Metabolomics is no exception. There are lots of different tools, which I am mentioning here, some open source, some commercial tools that allow you to do that, right? So why am I talking about pathway tools, and what does it have to do with sort of, the tools that we're talking about today? So the tool that we developed, Dinner, is actually a tool for cleaning up the data. Why is it required? And why am I talking about the pathway analysis here? Okay. So, well, first of all, it turns out that this pathway approach, I mean, although it works for metabolomics data, and we believe that it works because, we have our own tools that we developed. Many of you heard of it. It's called Netscape. It works, but it only goes that far. It only sort of, works for the known metabolites that map neatly to known metabolic pathways. Known metabolic pathways primarily cover what is called primary metabolism. Okay, if you go beyond that, for example, lipid metabolism is not covered by any of the pathway databases that you might know about, like, be it CAG, be it Reactome, you name it, lipid metabolism, we just don't know enough about lipid pathways. Okay. So the other reason why, and this is sort of, part of the reason why we need the tools that we're going to talk about, is because high throughput metabolomics studies, in particular untargeted LCMS studies, they generate a lot of data, and not all the metabolites and not all the features, as they're usually called in a data set, are readily identifiable. Okay, there are a lot of unknown compounds, unknown features in these data sets, and if you don't know what it is, most certainly you cannot map it into metabolic pathways, right? So that's sort of given rise to an alternative approach, which is data-driven. And so this is, again, very well known in the literature. People have tried building various sort of, derive the information about relevant networks from the data, directly from the data, and usually this is done through using some kind of correlation-based approaches. So what I'm showing here is basically this is a Pearson correlation network. As you can see, this is very dense because these are marginal correlations. This is a partial correlation network. This is not our work. This is from published paper, and so part of the problem with these is that they require relatively large sample sizes with partial correlation approaches, and so we have developed in the past tool and module for Medscape for handling these correlation networks. But the only reason I'm sort of talking about this is because when we developed this, we were all excited and we thought, well, this is going to be really great. And so we will cluster known metabolites and we will cluster them with the unknown metabolites. And hopefully it will help us to identify what these unknown metabolites are, right? So what I'm showing you here, as you can see, these are all amino acids, and there are a bunch of these things, this empty kind of nodes, empty boxes. These are all unknowns. So of course, naturally, we wanted to know what they are, right? So, and when we started looking closer, it turns out that, well, I mean, and they were really highly correlated to the known compounds. When I mean really highly correlated. And so it turns out that a lot of them were chemically related. So basically, you know, I'm showing you here proline, and so all these chemical formulas, you don't have to understand them, but just take my word for it. These were either various sort of, you know, fragments or, you know, otherwise chemically related substances that were related to the respective amino acids. Now, where does this come from? Okay, so here's a sort of, you know, quick primer on metabolomics. So basically, you know, what people are using and what we're using here in the metabolomics score, we're using so-called hyphenated techniques such as LCMS and DCMS. And so basically, you know, first you do, for example, liquid chromatography or gas chromatography, and that serves to, I mean, we're analyzing biological samples, which are very complex mixtures of different molecules, right? And so chromatography serves to separate these, and mass spec allows you to basically, you know, identify the determine the mass and identify what they are. So this is just sort of another useful kind of, you know, slide. This sort of, you know, illustrates the sort of, you know, point of sort of, you know, how chromatographic column sort of, you know, helps to separate these. And what we get at the end, I'm rushing through this because I really wanted to get to dinner, but but the thing that is really important is that the output of chromatography is chromatogram, which basically, you know, we have sort of, you know, on y-axis we have intensity, which is related to amount of particular sort of, you know, peak here, and retention time. So retention time is sort of is related to chemical properties of the compound, how long it takes to, you know, how long it stays in the column, and, you know, at what particular time it is eluted from the column, right? And then the other important point to make here is about mass spectrometry. So basically, mass spectrometer can only see charged molecules, right? And it cannot, if they don't charge, it doesn't see them. Have charged, it doesn't see them, right? So it has to be able to form an ion, right? And so what we are, even though what we are doing is called soft ionization, nonetheless, sometimes molecules break apart. Okay, hence various fragments and other things that we were. So it's a sort of, you know, even though it's a soft ionization technique, it still sort of, you know, breaks molecules apart and creates a lot of potential artifacts. Right. So now this is the essentially mass spectrum, and so from this we get mass to charge ratio, or MZ, and you're going to see that a lot. And again, we have intensity. Okay, so this is like, you know, my quick crash course on the LCMS, or liquid chromatography mass spectrum. Okay, so so basically what we just talked about is the fact that one metabolite, so as a result of this, one metabolite can be represented by multiple features, right? And this makes compound identification more difficult and creates the implications for statistical analysis, which I think Hani is going to mention on one of the next slides, maybe, right? So these are various sort of, you know, sources of redundancy, or, you know, degeneracy. That's another term for it. And so basically, you know, the breakdown, I mean, it's hard to, I mean, it depends on specific data set, but in general, I mean, you have, you know, fraction of known metabolites. So for example, in human plasma, it can be 400 known metabolites or something like this. Marina, is it a realistic number? 300-400, something like that, or whatever. And I mean, sometimes more, but, and so, you know, this sort of, you know, pool of unknown compounds, as it turns out, it is highly redundant, right? And so, I think with this, I can just, oh, you don't need that, right? So I'm going to turn it over to Hani, and he's going to continue.
All right. So to really restate the point, our goal for this software is to the greatest extent possible, minimize the redundancy in the data set. So as Alla mentioned, a single metabolite can give rise to multiple different features that we detect across samples. And so our goal is to really reduce this to a single most representative peak or feature for each individual metabolite. And as a secondary but also important goal, we want to also sort of get at what exact chemical adduct is represented by the underlying feature. So to just give a brief example, this is just a mass spectrum for one metabolite, tyrosine. So what we see is about 6 different peaks that all represent one metabolite. But we only want, say, this one, the protein peak, to keep for, and then just eliminate the others that are contributing to greater redundancy. So the main removables are your isotopes, such as this carbon-13 variant of the protonated tyrosine. We want to get rid of these additional adducts. These are sodium additions to tyrosine. And then, as Alla mentioned before, LCMS is imperfectly soft, and we do sometimes lose certain groups, such as an amine group and a carboxyl group. So these 6 peaks, we want to reduce it to just one individual feature, which is generally the most abundant one. So what properties are we going to use to sort of screen out these redundancies? So the first, as mentioned before, is that these chemicals that come from the same parent co-elute. So as Ella mentioned before, chemicals that elute within close to each other are chemically related, so the ones that are from the same parent are pretty much the closest in retention time. So then, also mentioned before is that there's a very, very high correlation between these redundancies, so that we can use and exploit to find. And then there's some kind of readily observed mass relationship, and by that I mean a difference between masses that we can use to sort of recognize certain adducts, such as the earlier sodium or the loss of amine or other masses that correspond to certain adducts. So that's sort of the motivation, and this is kind of the order in which we sort of detect certain properties of these redundant features. So this is the overall workflow. So from the input data, we have a retention time grouping step, a correlation clustering step, and then we try to use the mass differences between features to try to get at the underlying annotation for the chemicals that are represented by the features. So I'll just go through each and every aspect of it. So starting from the input data, so what we require is basically a table like this, where each and every row represents a feature, and what we just require is a name for each feature. It can be a chemical formula, a name that we suspect to be for the feature. It can be mass at retention time, or compound 1, compound 2. However it's named, it'll be treated the same. We just require that each feature be given a name. Then we require a mass in MZ format. Retention time, we generally expect it to be in minutes, and we also require at least 3 samples with measurements across. These are the sample intensities, which correspond to the abundance. There's no requirement on what order these columns go, and you can include additional columns. So Binner is pretty flexible in terms of what data tables we can use, just as long as you don't use special symbols, because we do have to read in the table. So just a brief quality control step before actually processing the data. So since we're going to be doing a lot of correlation analysis, it kind of helps to limit at this stage some of the missingness in the data. So as a brief first step, we sort of exclude those that have excess missingness by default over 30%. So that's a first reduction step. And so with those that remain behind, we just do a little bit of median imputation. And then also we have a recommended step of doing log transformation to just get our intensity values closer to something with normal distribution. So then we get to our main retention time grouping step, which is called binning. And so what we do is we basically segment the entire chromatogram into these self-contained units or bins. And we do this by first detecting, first we sort the features by the retention time, and we detect gaps in consecutive features. And if they exceed a certain gap, we end one bin and start a new bin. And so really this default gap right here, which is 0.05 minutes or 3 seconds, it's really perhaps the most important parameter that you supply binner, because it really is a way of controlling how big these bins eventually are. And so we chose 0.05 minutes as a, because we suspect that features that are more than that distance apart are generally different metabolites. And so using that, we sort of get different groups of features and put them into different bins in order to have a bit more efficient visualization, a bit more efficient downstream clustering. But you can already see from this step where we then take the pairwise correlation, already we see groups of metabolites that are highly related to each other, and we suspect eventually that these will be all part of the same parent. Eventually, we'll be doing correlation clustering to sort of detect these smaller cluster modules. But before we do that, we decided eventually during development that we had to treat one class of features a bit differently from the others. And those are our isotopes. So basically we do carbon-13 based scheme for isotope detection. So for each and every carbon that's carbon-13, it adds an additional Dalton to, or mass unit, to the underlying compound. So if this is the amino isotopic mass that we want to keep, each and every carbon-13 adds 1 Dalton to the mass. So about 1% of all natural carbon are carbon-13. So generally it tends to decrease for the total abundance of the compound with carbon-13 decreases for each carbon. So very simple rules that we use to detect, and this is all within one bin, I should mention. So they elute within a small retention time gap, and then they meet some correlation threshold, by default 0.6. They meet the assumption of dwindling intensity, meaning just that the intensity of each subsequent isotope is smaller than the one that came previous. And that works generally just because we have a small compound, so a limited number of carbons. So this assumption generally holds for metabolites, but unless there are isotopes of other molecules such as sulfur or chlorine, in which case it might affect the second abundance. And then one other very important thing that we exploit in this isotope detection stage is that when we find the difference in mass between two suspected isotopes, it can really be helpful for detecting the charge state on the compound. So for example, if it's a 0.5 Daltons apart, we have a double charged compound, 0.33 Daltons apart, that's a triple charged compound. And that's going to be really helpful later down the road when we start to assign chemical masses and chemical adducts to these individual features. So after isotopes are detected, they're sort of pulled aside and they become sort of bystanders, which then helps us do our clustering.
Does that happen before binning?
No, this happens.
Because the bin width was different than the isotope, the RT gap.
I'm sorry.
0.05?
No, the 0.05 is just to help us find the difference between the gap between one bin and the next.
That's what I understand. But this is 0.1, which is bigger, which means you could throw them into different bins.
I mean, in the end, you know, it's still within one bin. I mean, regardless of whether we detect it at this stage, it's just a default 0.1. But yeah, I think 0.05 or 0.1 would be sufficient to detect these isotopes. Okay, so with that, I hand it over briefly to Bill.
I could just clarify that real quick. The gap is just a gap we're looking for, but a bin may contain a much wider.
I understand that you have to have a gap.
Right, yeah.
Could,
but a bin could be anything from 1 minute to 1.5 minutes, because there would be no gap between 1 minute and 1.5. We have a continuous retention time of features there. That's why it's a little confusing.
Some bins can be quite large.
yes, I understand that. But you could theoretically throw one of those into a different bin.
No, because
It's done after the bin.
Yeah, because it's done after
well,
bin.
that's
Yeah,
what I asked
Which you asked and it didn't quite get answered.
Yeah,
Right.
Isotope detection is after binning.
Yeah.
I said within one bin. Okay, so I'm just going to briefly hand it over to Bill to talk about clustering.
Okay, is that good, Alex? Are we good? Good enough? Try again.
Switch all the way up.
Lights on. Try again. Okay. All right. So yeah. So Hani mentioned that we first separate all the features into bins, and at that point, there's an underlying correlation structure that we want to elucidate. And so basically, what we're trying to do here is look at how these compounds are related. If we have a bin that has multiple different features, but then we assume quite a few redundant features as well. And ideally, what we'll do is find some natural groupings. So the natural groupings we hope will be groups of redundant features that we can then annotate and eliminate redundancies. So when we started this whole discussion, which is a while ago, a little over a year ago, I guess, it was when we first started thinking about these things. We just thought, well, we'll get started. We have to do something to start with. We'll just do simple hierarchical clustering, and it seemed to work pretty well. Probably most of you run into that. I have a slide just to show what it does, but I think most people have seen dendrograms of hierarchical clustering, where you start with everything in a different cluster, take the two closest features, move them into one cluster, then you compare all the distances, the next two closest things you combine, and you just keep combining all the way up the tree. So it's really easy to implement because it's already been done in R by probably a lot of different people in different libraries. And Binner's written in Java, but I'm doing this a little more from a developer's perspective since it's tools and tech. Binner's written in Java, and we already have a nice framework for calling R from Java. So we thought that was an easy way, just plop it in there and it works. And it gave pretty good results. But then we started looking into it. Well, here's just a quick illustration again of the dendrograms. I don't really have to cover that. I think you all understand what hierarchical clustering does. We decided we needed something a little bit better. The problem with hierarchical clustering, and for us, is that you have to say a priori what the number of clusters is, and we don't know that. We prefer to have the data tell us what the number of clusters is. We came up with just an ad hoc way of specifying that number, but it wasn't really getting at the full structure. So we decided, well, we need something a little bit better. Well, we talked to our colleague, George Michaelides, whom Alla mentioned. He's a very good statistician, and he said, oh, we'll just do silhouette clustering. And we thought, oh, why didn't we think of that? Well, because we're not statisticians, but so we decided we had to look into this. silhouette clustering actually uses the data to determine the number of clusters empirically. So it seemed much more appropriate for what we're doing. So just very quickly, I won't bother to explain the math behind it. That is, in case you want to look it up for reference or have a reference to it, what a silhouette value is. Essentially, it's taking for each feature, how well does it fit into the cluster. So what silhouette clustering does, it starts with 2 clusters and does the full hierarchical clustering on that, sees how well everything fits, then it does 3 clusters and sees how well everything fits, and so on. And it chooses the best number of clusters based on those results. So what this formula is saying is that for each feature I, does it fit better into its own cluster, or would it have done, should we have put it somewhere else? Is it where it belongs, essentially? And that overall gives a measure of, when you start accumulating this over the entire, over all the features, it gives a measure of how well your clustering has gone. Hope that makes some sense. Obviously, we don't have time to go into a lot of depth, but keep in mind, just in general, this is already a lot more complicated because it's doing multiple rounds of hierarchical clustering and keeping track of it.
So all the hierarchical clustering methods I know do the whole thing.
Yes.
And so it seems like you should be able to do the clustering once and then move down the tree and say slice here, slice here.
That's effectively what silhouette clustering does.
Okay,
it looks
it's not actually doing the clustering.
It does the clustering. It does it at each stage of the dendrogram. It tries to find out how well.
Yeah, that's not the clustering's already happened because it's implicit in the whole tree.
That's right. Yeah, that's right. Yeah, you don't have to do. You don't repeat the process every time. You just look at every stage. That's right. So, as an example here, I'm not sure if this may be the one of the bins that Hani showed before, but you can see from the pairwise correlation structure of the heat map. This is something that Binner puts out automatically in the output. The red rectangles indicate very highly correlated regions. So if you count them up, it looks like 6 is a good number of clusters for that bin. So what we do here, K is the number of clusters. We calculate the average silhouette value, which was based on the formula I showed before. For all the clusters, take the average for each cluster, for the whole data set, given K equals 2, 3, 4, and so on all the way up. And you can see that, in fact, in this case, K equals 6 has the highest average silhouette value. And so that's what we choose. We decide, okay, well, K equals 6 looks like the best thing. And there's a plot that sort of illustrates here the singletons numbers 3, 5, and 6 here don't have anything to compare themselves to, so they automatically get a 0 value, but everything else gets compared. And it looks here like 6 is indeed the best fit. So that's a nice clean example. Well, they're not all that clean.
So you are clustering the rows?
Clustering the rows?
Are you clustering rows or clustering columns?
It doesn't matter because it's actually feature by feature, so it's a symmetric.
It's a square, even though it doesn't look like it.
Certainly, row is feature and column is sample.
So well, right. So originally, this is the correlation matrix. I should orient a little bit better here. What we start out with the input data is correlation is features in the rows and then intensities across the columns. So what we do is take each pair of features and correlate all of their intensities across all the samples. So for each pair of features, we get one single correlation value, and that's what each cell of this matrix represents.
And do you mandate that a cluster from this clustering algorithm must be continuous in terms of retention time?
Yes, right. So a bin is going to be a stretch of retention, fairly narrow, we hope, stretch of retention time.
No, bin must be continuous,
Yes.
but the clusters.
No, so they don't necessarily. It's a good point. They don't necessarily end up continuous in retention time because now what we're doing is taking everything in the bin and just looking at the correlation structure. So whatever the clustering algorithm tells us, it actually does tend to shuffle things around a little bit. And so it's no longer necessarily sorted by retention time at that point. But what we're looking for now, so we've already sort of used retention time as one measure of similarity, and now what we're doing is looking at intensity as another measure and the correlations between intensities and using that measure of similarity to further identify redundancies. So we're sort of going at it one dimension at a time, and this is the second dimension that we use. So I'll have to, I hope that answered to some extent. So I'll have to keep moving on here. But at any rate, so there are always catches. It's never as simple as it seems. So we had to do a little bit better than just the straightforward silhouette clustering. Problem is, well, this is when Jan, who's the co-developer on the project, started looking into this, and we realized that the unweighted silhouette clustering that I showed tends to choose k equals 2, just the 2 cluster case, way too often, or doesn't really get at the structure. And there's a weighted silhouette clustering in the literature as well, but the idea is to downweight the value of large clusters to avoid this k equals 2 problem. And the problem is it tends to do too much, and it oversplits, and you end up just sort of splintering the whole thing into, at least for our type of data, into a whole bunch of different clusters, way more than you actually want. So Jan came up with a sort of parametric model that allowed the weight in the clustering to vary from completely unweighted all the way to weighted. And then what we do is calculate across a grid of weights. We do the entire silhouette clustering, and then it finds what the best one of those weights is. And so we think that really is doing a nice job now of elucidating the correlation structure. But implementation is always a question. So it's obviously, from what I described, way more computationally intensive than just simple hierarchical clustering. Could have used R to do it, but it's way too slow. And this is a good point for anybody who's tried to struggle with R and thinking there's got to be a faster way. Well, higher level languages are a lot faster. I was surprised to find out this actually, that Java is actually typically 50 to 100 times as fast as R if you do it carefully. I'm an old guy. I started out in C, and hate to admit it, but I actually had to learn Fortran at one point too. And those are really fast. So they're still valuable, C++ and Fortran. Probably a little bit better than Java. So if you're really in a critical application, they might even be better. But for what we're talking about minutes, not hours or days. So Java was what we were already writing in, and it made a lot of sense. So we implemented it in Java. And now we've taken, what we're trying to do is, it's supposed to be an interactive tool for exploration. So if it took 2 hours to do the clustering, it's not the end of the world, but you're going out, getting a cup of coffee, walking the dog, and you come back, it's not really interactive. But we implemented it so it takes maybe 2 minutes, and that way you can really get your results, reset some parameters if you want to, run it again, and it is much more interactive. So that's just sort of a little bit of insight into some of the challenges in actually implementing this stuff. And back to Hani.
All right. So now that we've grouped it by retention time, we've grouped by correlation. So now we have a step to finally try to get at what the underlying chemical addicts are. But before that, we calculate the differences in masses between features that are within the same cluster. And we have basically a way of just showing this in the spreadsheet, where differences in masses are shown, and very commonly recognized differences are highlighted in their own color. And those are based on mass differences that are very commonly seen. For example, the difference between a sodium adduct and protonated adduct is 21.98. An amine group is about 17.02. So over time, using this tool and looking at the chromatography, you sort of recognize a lot of these very common mass differences, and that is the first step to helping you understand what adducts or chemical groups are in the data. So this used to be the only way for which we used to screen out different adducts, but it turned out to be not enough. So for our annotation, for more complex, for example, multiply charged adducts or multimers, it became apparent that we not only had to find differences between different features, but we also had to find it with respect to some hypothesized neutral mass. And this is sort of the solution that we are trying to implement and that we came up with. So first we divide our annotation file into a set of what are called charge-carrying adducts and what I call neutral additions or losses. So what these charge-carrying adducts do is they help you form a hypothesis for what the underlying adducts are in the data. And then these mass differences are sort of used as a way of complementing the adducts that you previously found. So I'll just walk through a brief example of how that works. So just the annotation procedure. So to begin, we just choose the most abundant feature in the cluster. And that generally is going to be the feature that best represents the underlying metabolite. And from that, we obtain a hypothesis on what the neutral mass is for that adduct. So just to show this, this is the most abundant feature right here, and here are just two isotopes that are kind of bystanders. We're not going to do any further annotation on them. But first we say, okay, could this be a protonated adduct? If it is, this is the neutral mass that we detect, and from that we get only one adduct hit, which is basically just this same M plus H. And so we keep doing this for other hypothesized charge-carrying adducts until we get the one with the best hypothesis, the one that gets us the most adduct hits. So, for example, we next try this as a sodium adduct with a base mass of this minus a sodium mass, and we get a total of 3 charge carrier hits, which just so happens to be the best hypothesis for this particular cluster. And then once we come up with what we think is the best hypothesis, we use the mass differences that we previously computed to come up with the remaining hits. So we previously detected this, this, and this from the best hypothesis, and then from those that remain, the differences in mass between this and this and this and this help us find the remaining based on the second class of annotations, which were in the second part of the file. So that's generally a very simple example of how we do this detection. And the reason we did this is to be able to detect more complex adducts, such as the multiply charged, when we have multimers, and just to get at the best hypothesis for what the most abundant feature is. Okay. But now I hand it over to Bill to talk about a bit more building our annotation file.
Okay. Right. So the whole purpose of, well, one of the main things that we think stands out about Binner compared to some of the other tools that are doing similar things is that we're trying to be really interactive, and we're trying to let expert chemists like Maureen in particular just basically driving the whole process of sort of each subsequent step that we take is in response to something that Maureen finds in the actual data for the metabolomics core. And so that's been partially possible because we have an annotation file that allows someone to start with, well, we started with a fairly simple file, just a few basic annotations, and I'm sure Maureen quickly brought it up to a lot more than that based on what she knows. But then she's even admitted that there were a few that she didn't know about ahead of time that she found through using our analysis. And so then the idea is that over time for your own platform, if it's an individual platform, you can keep adding more things to the annotation file and get a more complete set and more accurate set of annotations as you go. So you don't have to be really knowledgeable starting out, but ideally if you're using the program, you will become more knowledgeable about your own data as you go. And so that's what we hope that's a really useful feature. But there's sort of a question, if you're using our program with your annotations in it and we're just outputting based on those annotations, then how are you actually going to learn anything more? You're just getting what you put in. Well, so there's, and this is again something that Jan wrote, came up with, but there's an output tab that we have that basically does a distribution of the entire data set. What are the common mass differences that are found in the data set? What mass differences just happen to show up more frequently than you'd expect by chance? Some of those you may have already known about and may have annotated or put in your annotation file, but others may be completely new to you. So then here's an example of what that can look like. It's probably a little small, and I'm not sure how easy it is for everyone to read that, but the idea is that basically there's a distribution on the side where each little cross mark indicates a certain number of that mass difference in the data set, and only things that are much more likely than chance are displayed here. And what you can see then, each color represents sort of a continuous mass, little range of mass. You can see it's done down to thousandths of a Dalton, so it's pretty fine grid mass, or grid, fine grid. So basically from 46.985 down to 994, there are a total of 285 hits, as you might call it, that are very close to that mass. Well, that happens to be something that was already in the annotation file. It's hydrogen plus 2 sodiums. Then down at the bottom, another one that's based on what, as Hani was saying, a neutral mass difference. Again, it's annotated. But then in the middle, there's this 50.015. Shows up a whole lot. No idea what it is. Not annotated. But if you find that, if you see that, you probably want to look into it and decide, is that something I want to put in my annotation file, or is that maybe something that is commonly occurring and because of chemical properties and is not something that's a redundancy, but at least it gives the investigator a chance to explore based on what's actually in the data. So it's just an example of how we try to give people a chance to grow as they use the program. And I think, well, we may or may not have time for a demo, but we may have a little bit of a chance. But you might be asking, well, how well does this whole thing work overall? So before showing output, just have a quick comment about the performance. And this is, we are still in development, so these are very vague numbers. And it obviously does depend on the data set, but de-isotoping we typically get from 10 to 20% reduction, and we're not the only ones doing de-isotoping. A lot of people do that, so that's sort of cheating in a way, but it's important to do that first before doing the annotations. And then after that, we get anywhere from probably, of the remaining features, probably 10 to 40%. It really depends a lot. Again, we're being interactive here. We have a lot of parameter settings. You can be either more aggressive or less aggressive in your annotations. The more aggressive you are, the more annotations you get, but the more false positives you'll get. If you're less aggressive, then you probably are more toward the 10% range, but you can rely on those annotations more strongly. And we're still going, so we may get further. There's still a lot of structure that we haven't really elucidated. If you start looking at all the patterns, we're all going nuts just looking at the patterns. They're everywhere, and it's really fun to look at it. But we think we're doing pretty well compared to what's out there right now, and so we're putting together a manuscript and hope that it will be reviewed soon. But that's a lot of reduction. I mean, basically, there's just a quick story I want to share that's not on the slide, but something that Maureen shared recently was another group that had, was it 15 or so significant metabolites? So when people do these analyses, it's usually a disease versus a well group or something like that. And so t-tests or something are performed, and what they really are interested in scientifically are what are these significant metabolites? What might be driving the difference between the sick and the well people? Well, so we give them, the Corps gives them a list of, or wherever they got their samples done, they get a list of the most significant features. In this case, I think there were 15 top hits, as they're called, 15 metabolites, one of which is glutamate. Well, turns out actually 10 of them were glutamate. They didn't know that. So they were basically thinking they had 15 different compounds that they had to investigate. In fact, when we annotated it, we found out that one of them was glutamate, 2 of them were isotopes of glutamate, and then 7 more were pretty easily annotated adducts or variants of glutamate. We and Maureen actually, but so that just shows you that you can't really trust your hits in this kind of data to be independent of each other, and it's really important to look at the redundancies to try to decide whether you actually are looking at what you think you're looking at. In this case, they really only had probably 6 independent hits, and maybe they wanted to go a little bit lower in their p-value distribution to find some more. So we hope that's one of the other values besides just reducing the overall number of metabolites. And Paula, do you want to talk about these, or?
Sure. So right now,
So right now the output of Binner is an Excel file. I think it has been mentioned throughout the talk. It's not just an Excel file. I mean, it's a pretty complex Excel file at that. I mean, it has multiple tabs and all the heat maps and all the sort of, mass differences and, all these things are sort of, already formatted or, colored in it and so on and so forth. And so, I mean, I guess on one hand, this is great because, I mean, I guess, as we all know, scientists like to work with spreadsheets. It's convenient, it's familiar interface and so on and so forth. I mean, there are some things that we think would be potentially, if we create a sort of, fully interactive environment, like in Java, for example, then, potentially we could provide access to spectral data or, basically look at the peaks. And so one example here is, I mean, we didn't really talk much about outliers, but I mean, so we're looking at sort of, multiple samples, right? And so before it ever gets to Binner, the program basically, has to go and sort of, align all this sort of, peaks in different samples, right? And so here is an example of well-integrated peak, and it's fine. But on the other hand, on the right, there is an example of a poorly integrated peak where it just sort of, cannot decide, the program cannot decide which one is the right peak. And as a result, I mean, it affects correlations, it affects retention times, right? And so, I mean, if you look at it, and especially if you're trained to look at this data, so for example, Maureen can look at them and say, well, what, I don't believe that integration, I'm going to do it manually or whatever. But I guess, it affects your, and I mean, in general, I guess, we have some examples where Hani looked at outliers and it affects it. So, so this is just sort of, some examples of the things that we think could be handled in a more sort of integrative, sort of interactive environment. So that's sort of, at least one idea. So I think I'll just stop here and just want to emphasize again that none of this would be really possible without sort of, working side by side with Metabolomics core, and a lot of ideas really, came from Maureen, and all we had to do is basically, or Bill had to do, and Jen had to do to try and figure out a way to code the certain sort of logic into it, how we would want to reproduce the analysis that people would do sort of semi manually, which is not a trivial exercise, but it's not the worst way to develop software. So I think I'll just stop at that. Thanks. Yes.
I have to reveal my ignorance here in my question. But so in the example that Bill gave where you identified 10 variants of glutamate that were actually all glutamate, not 10 different things. Maureen, do you go back to the bench then and validate in a way that's completely independent of Binner to say, yep, sure enough, I got 10 variations of glutamate?
So what we're doing right now, there's a few ways we're trying to do that through, some of it is by looking more carefully at the isotopic patterns, because certain adducts that are forming are going to have a very distinct isotopic pattern compared to the parent ion glutamate. There are some other really obvious things that, well, obvious if you are mass spectrometrists, that are happening when you look at trends in sort of the what's called the mass defect. The number after the decimal place, after the integer, to kind of show that it's very unlikely that a metabolite with that mass defect would occur at the same time as glutamate. So there's some other things that we're doing to sort of validate that, but it becomes very difficult to do that on the bench because, first of all, these are transient things. It may occur, an adduct may occur on glutamate today. If we ran that tomorrow, it may not, because it happens in this source in this very high pressure and high voltage environment, so they're always changing. But so those would be a little difficult. And then the other thing is, for example, I mean, you could do MS on, say, like neutral loss peaks where you have a fragment and prove that that fragment is that, or if you have an instrument that can do MS to the third, for example. So there's definitely ways of doing it. But again,
I was thinking of a technology that's independent of mass spec.
Oh.
So for gene expression studies, we find a gene that's differentially expressed using sequencing technology. You know, you come back to it with qPCR, and because it's an independent technology, or at least quite a bit different. Is there,
it was
is there
really
a way to
interesting.
do
We were
that?
just on a conference call before this where we're looking at another lab's data, and what we think is some fragment ions of something like phenylalanine, for example, and one of them that comes out has exactly the same mass as benzene. And so the question was, like, how do you know if that benzene isn't part of an environmental exposure, and that's really there instead of part of phenylalanine? And so you could think of a way that you could, do some sort of an exposure study where you could say, look, this one has a benzene exposure, and it doesn't vary compared to this one. So that's really, I mean, that would be an expensive way of doing it, but that would be one way. And then the other thing we had talked about.
I was going to mention something else. So just because we sort of happen to be part of several large consortia, Marine spent a lot of time. I mean, there were ring trial data from a couple of them. She can tell you about it. I think it's also valuable. I mean, basically what it is different labs that have different instruments. So I don't know if it sort of, passes for independent validation or whatever, but they can have completely different platform, but they're running the same set of samples, right? And so, I do want to.
No, absolutely. I mean,
So basically, Maureen was able to show that, it's extremely unlikely that if you're using completely different chromatography and a different instrument, they're seeing the same highly correlated features. And so I think it sort of adds confidence to the identification here. And so.
Yeah, so that example where they had annotated something as benzene and it was collating with phenylalanine, that was seen in one mass spec platform where they were doing helic chromatography, and we were using reverse phase chromatography. So chromatography is so different. The fact that we both saw both of those peaks at exactly the same time is very unlikely. I mean, and that wasn't just 2, it was like 6. Because chromatographically, benzene should separate from phenylalanine in my platform or in theirs. I mean, in one of the two. I don't know which one would be more likely to separate in, but it would in one of them it should have.
But Maureen, if I understand this correctly, benzene is benzene, and you cannot tell if half of that benzene came in fact from environment and the other half came from as a breakdown product of phenyl. It's not a situation where you have, you can tell that you have some bacterial sort of DNA or RNA present in your sample because this is not human DNA, right? There is no such thing.
The only way you can tell it is through chromatography. If I inject an authentic benzene standard and it comes out at 2 minutes, but I'm getting a peak that says it's benzene and it's coming out at 3 minutes, and the thing at 3 minutes is not benzene. So it's just, we can validate it in certain ways.
Yeah.
Do you report at all the very early in the process, if it wasn't in 30% of the samples, you chop it? Do you report those somewhere?
Yeah, we
because
have a report tab at the beginning to report.
Because those might be interesting if they're abundant, and depending on how big your sample number of samples is and stuff.
So my future better version that would be to be able to specify groups as well, and say we want to only do data reduction using any sort of absence or presence cutoff within a group, because something may be present entirely in one phenotype and not in the other, and you don't want to get rid of that. So 30% can, if you have 50-50 samples, it can get rid of it. But most software doesn't do that yet. Still, even the instrument software, they don't do that effectively. So it's something that we would do.
I mean, there are programs, data downstream analysis programs that allow you to do that, and I mean, so anyway, so what Bill is showing is.
Yeah, so this is the summary tab that we provide. Basically, you can see that we do report how many, in this case, there weren't any missing values, but we report any that were. We don't actually list them. It's a fair question. People might be interested in seeing that information. We're still expanding what we have in the summary.
Yeah, especially if they had reasonable signal strength.
Right, and so there's always the question of is that a biological signal or regular or just detection?
What's even more alarming though is if you go and look at a database like Metabolomics Workbench, that very few people report any pre-processing they do. So you can get a lot of data and not know what has been done to it. And
magic.
Yeah.
But I think it's useful because I cannot remember 2 weeks from now I'm not going to remember what it was, and Maureen has so many of these, so it just would be impossible.
Oh no.
Can you click on it?
Yeah, sure. Don't zoom too much there. Okay, yeah, so, sure, so I showed the mass difference distribution, so that was a screenshot from the output. We do that, generate that automatically. We have here compounds, mass, and retention time. The mass, retention time, and intensity are the three things that we use to do all of this. And then, as Hani mentioned, there are some other columns that you can bring along. This is a Kendrick mass defect that's used in other, to look at contaminants, I guess mostly is probably the biggest use right now, but other things as well. Anyway, then we show our annotations and sort of the math of how what those masses correspond to, the clustering arrangements, and then the correlation heat maps basically for each cluster. And so there's some visual aid here if you're looking at a big data set. The green for isotopes, the green are the base isotope, or the base of the isotope groups, and then the blue are any of the isotopes we find. And then similarly in the annotation part, green means the base adduct or the molecular ion, and then the yellows are the sort of derivative secondary annotations. So we try to make it a little easier to scan all this enormous amount of data.
And it's so much easier on a big screen.
And it's a lot easier. and then what's another, let's see, I'm trying to think if there's something else that's interesting.
Mass differences, maybe?
Right, well, the mass differences.
No, like a matrix.
Oh, the matrix, sure. Yeah, I'm trying to, the arrow's not where it's supposed to be here. It's going to screen problem or something.
That's okay.
So, command left click. Okay, I'll listen to that, I guess. Try it. Oh, yeah, so unfortunately, because of the resolution here, I'm unable to get from one to all the tabs at once here.
We should probably wrap up anyway, since we're a little over the hour. Maybe take the rest offline.
Sounds like a plan.
Thank you.